Welcome back, Calculus. This is going to be related rates day 2. Up on the screen here, we have a nice joke. If you get it, you get it. IYK. So today we're going to solve related rate problems. We're going to do a little substituting before we differentiate, or just solving for, or having to do a little bit of algebra before we solve. So before we start, just some formulas that we used last time. We used area of a square and area of a circle. We're going to need these formulas to relate these different quantities together when we make our related rate relationships. So as a review, area of a circle is pi r squared. Area of a triangle is 1/2 the base times the height. The area of a rectangle is just the base times the height. And the area of the square is side length squared. Volume of a cube, that's going to be side length times side length times side length cubed. For a general prism, you find out whatever the area of the base is and multiply that by the height. So for example, a cylinder, if you have a cylinder, this is a prism with a circular bottom. The base area is a circle, so the area of the base is pi r squared, and then the height is what you'd multiply by to find the volume. To find the volume of a cone, it's going to be very similar. So you take the area of the base, which is a circle, multiply it by the height, but then you got to take 1/3 of that. It's not that full thing, it's 1/3 of that volume. And the volume of a sphere is 4/3 pi r cubed. So those are formulas for volume. Surface area problem. So surface area is if you were to cover or paint the outside of a three-dimensional solid, how much paint would you use? How much area do you use up? So a cube, think of a dice. A dice has 6 sides. Each of them is a square. So if I wanted the area of one side of a dice, that's just s times s. So s squared. Now there's 6 sides of a dice, so you're going to multiply it by 6 because there's 6 of them. And that's how you find the surface area of a square. For a prism, I'm going to make a rectangular prism. Oh yeah, let's try making a nice one. So there is 6 sides, but they don't all have the same area. So if I just took the area of the front door, so to speak, that's a rectangle. So I'm going to call the dimensions of this length, width, and this will be the height. So the area of the front window is length times width. Now the back window is going to be the same thing. That's also going to be length times width. So there's going to be 2 of those. Now that's not all of it, so we got to add something. Now these side doors right here, the area of that is going to be the width times the height, and there's 2 of those side doors. So it's 2 WHs. And then you kind of have the ceiling here. Now the ceiling is the length times the height. And there's also a floor, so there's a ceiling and a floor, so there's 2 of them. So that's how you find the area of a rectangular prism, surface area of a rectangular prism. For a cylinder, so if you kind of go back to this shape right here, there is a circle on the bottom and a circle on the top. So there's 2 circles, so 2 pi r squareds. And then you have the walls of a circle, and the area of the walls of a circle is 2 pi r h. And we can talk about that a little bit later in class, why that actually is that. And the surface area of a sphere, so a sphere, by the way, is like a ball, is 4 pi r squared, actually. So other stuff that we'll look at later is Pythagorean theorem, a squared plus b squared equals c squared, and similar triangles. We'll look at that one today. But those are some formulas that we're going to need in our pockets. Quick review from last time when we're doing related rates problems. Start off by drawing a diagram, label the relevant information, defining calculus terms that we need, come up with a formula to relate the information we have, differentiate, and then substitute and solve. So, example 1. Farmer Brown is filling... I like doing this now. Nope, not that. Farmer Brown is filling his pig trough, which is 24 by 3 by 2.5, with slop at a constant rate of 12.5 cubic feet per minute. Determine the rate at which the depth of the slop is rising when the slop is knee deep, 18 inches. So, in this situation here, when we fill up the tank, just recognize first that the length and width, no matter how much you fill up, are not changing. Those are constants. So the length, which is 24, and the width, which is 3, are both constants. They're not changing. So I'm going to plug them in not as variables, but as actual numbers. I'm given that it's filling at a constant rate of 12.5 cubic feet per minute. That indicates to me that this is the rate of change of the volume, because it's cubic feet per minute. So the rate of change of the volume over time is 12.5. And it's positive because we're filling it. We're trying to find out at which rate the depth of the slop, the rate at which the depth of the slop is rising. So we're looking for the rate of change, and we call it the height instead of the depth over time. That's what we want to know. So what formula can relate volume to height of a rectangular prism as we see? And that's going to be the volume of this container. This prism is a rectangular prism. The base is a rectangle, so it's length times width. That's the area of the base that we multiplied by the height, which is h. So we are length, width, and height. Now, like I said, the length is 24, that's a constant, and the width is 3, that's a constant. So I could really just write this as 72h. Now, if I differentiate both sides, I get that the rate of change of the volume is whatever the derivative of this is, which is 72 times the rate of change of the height. Okay. And so if I plug in what I have, I know that dv dt is 12.5 equals 72 times dh dt. So to solve for dh dt, I just divide both sides by 72. And that gives me that the rate of change of the height is, 1 second, about I'm going to go with 17 feet per minute. Okay. So one thing you might recognize here is that I never used we never actually found out when it was, what the rate of change when the height was knee deep. And that's because this part right here, let me do it in a different color. The volume is 72 times the height. The volume is a linear function, and the slope of a linear function is going to be constant. So it makes sense that the rate of change will be constant, regardless of whether it's empty, whether it's knee deep, whether it's almost full. It's always going to be filling at a constant rate, and that's what that constant rate is. Okay. Here's another example. Let's see what we come up with here. Sand is being poured from a conveyor belt onto a conical pile of sand at a constant rate of 330 cubic feet per minute. After several minutes, the pile measures 22 feet tall and 12 feet across. The project foreman wants to know how quickly the height of the sand will be rising when the pile is 36 feet tall. So right there, I know that we're trying to find the rate of change of the height when the height is 36. Now we're given that it's being filled at a constant rate of 330 cubic feet per minute. Again, cubic feet per minute indicate to me that that's the rate of change of the volume. And it's being filled, so it's positive 330 cubic feet per minute. Now, when we're talking about cones, the dimensions you generally look at are the radius and the height. Now, at some point, we're told that the pile measures 22 feet tall. So at one point, it's 22 feet tall. and it's 12 feet across. Now, 12 feet across means that the radius is really going to be 6 feet. Okay? And I'd rather use the radius. Now, I know at some point it's 36 feet tall. And what a lot of people try to do here is solve for when it's 36 feet tall what the radius is. And you could figure out what the radius is, but I'm not asked for that. I'm asked for the rate of change of the height, not what the radius is when it's 36 feet tall. So that's just something that people tend to do that's unnecessary. Back to the problem here. What is my formula that relates volume to height? And simple enough, the volume of a cone is 1/3 pi r squared times height. Now here's an issue we just ran into, is if I take the derivative, the radius is not a constant, nor is the height. As you keep pouring sand, the radius is getting bigger and the height's getting bigger. So if I were to do a derivative here, r and h are both functions of time, I would need a product rule. And in the course of the product rule, I'm going to have an r prime and an h prime. So then I'd have now two variables in a single equation, and I wouldn't be able to get a solution. So what I'm going to need to do here is try to rewrite the one of the variables in terms of another variable. I want to write r in terms of h or h in terms of r. So you have to recognize that regardless of what the at what moment in time you're looking at the radius and the height, it's always going to have the same ratio. So the radius to height ratio is going to always be the 6:22 ratio. These two triangles are similar triangles. They both have 90-degree angles. In fact, all their angles are going to be congruent. So the ratio between the radius and the height has got to be 6:22. Now, just to make numbers smaller, I'm going to rewrite that as 3:11. And so that's the ratio from the radius to the height. Now, if this is true, then I can multiply both sides by h, which will allow me to isolate r. So now I can rewrite the radius as 3/11 h. That is what I need, and this is probably the most trickiest part in this problem. And by trickiest, I mean this is the part where a lot of people make mistakes, is actually that substitution step. I need to find a way to write the radius in terms of the height, because now in this formula right here, I can write it in terms of v and h only. So it's 1/3 pi r squared times height, but I'm not going to write r, because r is equivalent to 3/11 h. Okay, so that's a very important part. And now from here, it's just some algebra, and then we're going to do some differentiation. So first, let's clean this up a little bit. This is going to be 1/3 pi. Now 3 squared is 9, 11 squared is 121, and h squared is h squared times this h that's outside. Now 3 divides out with that 9, so that becomes a 3 up top. And h squared times h is going to be h cubed. So I'm going to have a 3 pi, I'm going to write 3 first, 3 pi over 121, and then h squared times h is h cubed. Now that I have an equation that relates the volume to the height, and it's all in terms of one variable, now we can differentiate both sides. So I'm going to ddt both sides. So now the rate of change of the volume with respect to time is whatever the derivative of the side is. Now the only thing you really need to worry about is this h cubed, right? The derivative of h cubed is going to be 3h squared times dh dt, which I'm just calling h prime. So I'm just going to multiply by 3. 3 times 3 is going to be 9 pi over 121 h squared times h prime, which I'm writing dh dt over here. So again, not a hard derivative. It's just h to the third. It's going to be 3h squared, but I know there's some fractions and pi in there, so it can be a little bit intimidating at first. So at this point, we know what the rate of change of the volume is. So we know what this is. We know it's going to be when the height is, I believe it's 36. So when the height is 36, we can plug that in. And then we're just going to need to solve for dh dt. So we're going to plug in here. The rate of change of the volume is 330. That equals 9 pi over 121 times h squared dH dt, and we know that we want this when the radius is 36. Okay. So let's see here. To get rid of this fraction, I'm going to start off by multiplying both sides by 121. That'll just delete that for me. So 121 times 330 is 39,930. Now I still have a 9 pi here. Now 36 squared is 1296. dH dt. 1296 times 9 is 11,666. Or 64, excuse me. Times pi, dH dt. Now to solve for dH dt, we just got one more step. We're going to divide both sides by 11,664 pi. And we finally get that the rate of change of the height when the height is 36 is about, I'm going to round this, 1.09 feet per minute. So about a foot per minute. Anyway, so that is a fair bit of algebra and arithmetic. But again, very important part here is to rewrite the radius in terms of the height and do the substitution step. And then even doing that, although that's the most important part because that's how you kind of like get started, there's still a lot that comes after that. You still have to simplify, you still have to differentiate, and then you have to plug in, and the numbers can be messy. But it's all, it's part of the grind. It's all in good fun. Here's one more example, and then we'll be done. Sand is being poured from a conveyor belt onto a conical pile of sand. Sounds familiar. At a constant rate of 330 cubic feet per minute. Sounds really similar. After several minutes, the pile measures 22 feet. This is like the same problem and 12 feet across. Determine how quickly the radius, the radius of the pile when it's 36 feet tall. So at the same moment in time, we're just interested in what's the rate of change of the radius. Now, we could go back and do this whole thing again, but instead of solving for r, we can solve for h and do the whole shenanigans. But because we already know what h prime is, that's going to save us a lot of time because this relationship here is good enough. Because if we want to find out what the rate of change of the radius is, and I know what the rate of change of the height is, this formula right here relates them perfectly with a lot less algebra. So if the radius is 3/11ths the height, then we can just ddt both sides from here. So the rate of change of the radius with respect to time is going to be 3/11ths times dH dt. So it's going to be 3/11ths times that 1.09, I believe is what we got. Yes. So it's about 0.297. I believe it's feet per minute. Let me just make sure. Feet and yeah. So if you saw this problem and said, oh boy, we're going to have another long problem to do, we saved a lot of time doing the first problem. So that made this problem a little bit easier, as long as you recognize that, hey, wait a minute, we already have a relationship here between r and h, and I already know h prime now, so that makes it a little bit easier. Anyways, if you made it this far into the video, I hope you like, share, and subscribe. Make sure to ring the bell for notifications. It really helps the channel. And go Lancers.